Okay, we're going to get started. It's 9 o'clock. So thank you to those that joined. Just want to disclose that this is being recorded and it's going to be shared throughout the dealer network. So today we're going to be talking about advanced defrost. If you have a question, please type it in the chat. Cam will let me know. So why do we need defrost? Well, in order to absorb heat energy from outside, the outdoor coil has to be colder than ambient to absorb that heat energy. And in many cases, that means that outdoor coil is going to be below freezing and you're going to develop frost on it. So this is a picture of a perfectly frosted unit, likely just about to enter a defrost cycle. That is not a system that is improperly running. This is exactly what you should see on a cool, humid day. It's going to build frost up like this. In this case, it's built up evenly, which is a good thing. And this isn't a frozen unit. This is just a frosted up unit. So this is completely normal. We use two sensors to decide whether it needs to go into a defrost or not. So this is a demand defrost system. You'll see this on all Trane unitary equipment and most ductless equipment, where you're going to see two sensors, one of them being an ambient sensor. This is our older version of the sensor. And as you can see, sometimes it could be hanging down or tucked this way. So it was changed to this sensor in the last few years so that it was always in the exact same spot for consistency. One thing to consider is that outdoor ambient sensor does play a big part in whether it decides to defrost or not. So you want to make sure that it's not in direct sunlight, it's not in front of a bathroom fan vent or something that's going to be affecting the temperature. Even having the insulation pulled back on your larger pipe, your vapor line, because that can be hot in heating mode, could affect this. Okay. So that works in conjunction with a coil sensor. This is the older version of the coil sensor, where it was pushed into a tube connected to the bottom circuit of the coil. So a few things were issues with these. Sometimes they would fall out and you would have to put a tie wrap here so it wouldn't fall out. Sometimes it was touching this edge, sometimes it was touching this edge of the tube, and sometimes it was in the middle, not touching any edges. So again, there was some inconsistencies there. So they started using this sensor. And if you order replacement sensors for either of these sensors, the newer sensors are what is going to show up. And this one clips to the pipe, and only this portion of it is sensing the temperature. So in the case of a replacement, you would just clip it next to where this tube is. So how those two sensors work together. The orange line is ambient, and the gray line is what the coil temperature would be seeing. This is through some runtime and two defrosts. So what happens is, as the coil frosts up, the coil will get cooler and it'll become less efficient. So as it becomes less efficient, that coil sensor is reading a colder temperature. And once that delta reaches a certain point, maybe 10 to 20 degrees delta is where it would trigger a defrost. A normal operating system without frost would be about 7 degrees delta. So as you can see here, they start at the same temperature. Ambient remains relatively consistent. It does fluctuate during the defrost. But you can see the coil temperature slowly getting colder and colder and colder and colder until such time as the system says, okay, we've become inefficient, it's time to defrost. So it goes into a defrost cycle. That coil temperature rises to 32 Fahrenheit roughly. And that's because At 32, it's going to stop there until it can melt the ice. All of the heat generated in the outdoor coil is going to go into melting that frost. So it won't go up in temperature until the frost is gone. So you can see it kind of sticks at 32, and then it shoots up, and once it hits 47, it's going to terminate the defrost and then go out of the defrost cycle and start it all over again. When that coil starts to frost up, gets colder, goes back into a defrost. And that's how it triggers it. It's going to aim for a defrost cycle of 4 minutes, has an adaptive learning algorithm. So if this defrost process takes longer than 4 minutes, it's going to tighten up this delta. If it takes less than 4 minutes, it's going to let it go to a larger delta before it initiates a defrost. So both sensors are important because they're going to be a delta between the two. So we have our defrost board, and this is the basic layout of it. We have a relay here that the outdoor condenser fan goes through. This can cut the condenser fan during a defrost, which we'll get into. We have our 24-volt wiring harness with your R, common, Y, O, and X2. We have our low pressure switch that plugs into the board. The reason that needs to happen is so that it can populate an error code on the fault status, the fault light, which is red, and also so it can count the low pressure switch failures, so that once it reaches a certain number, it's going to go out into a hard lockout until there's a reset in power. We also have the coil bottom sensor or coil base sensor, which is the yellow wires. And then we have the black wires, which is the outdoor temperature sensor. And then we have our forced defrost pins here, and a couple of jumpers we'll go over. Another thing I want to show you guys is the chart that you can find in service facts. So in that envelope in the service door, there's service facts, and you'll see this chart somewhere in the middle where you'll see defrost is only enabled when it's less than 52 Fahrenheit outside. That's because if it's less than 52 Fahrenheit, you could potentially be frosting up your coil, right? Because that coil could be as much as 20 degrees colder than ambient, which is freezing. So it can't go into a defrost when it's above 52 Fahrenheit. It also can't go into a defrost unless the coil is colder than 32 Fahrenheit, because that's the temperature you can develop frost on it. And these are just to boost efficiency, because a defrost cycle is inefficient for the system as a whole, because it's running that outdoor unit essentially in reverse, taking heat energy from in the house and putting it in that outdoor coil. So you have a minimum defrost time of 1 minute. So that means if it initiates a defrost, regardless what the sensors say, they could say that it's over. It's going to continue to defrost for a minimum of 1 minute and a maximum time of 15 minutes, regardless what the sensors say. The target time is 4 minutes. So it's going to adjust that delta based on the previous defrosts in order to target a 4-minute defrost time. The defrost termination temperature, so this is the temperature that the coil gets to before it says that the defrost is over. Factory is 47 Fahrenheit. And the high termination, if you were to cut this jumper, is 70 Fahrenheit. The switchover relay valve delay is 12 seconds. So that means that the outdoor fan, when a defrost is about to finish, is going to turn on for 12 seconds before the switchover valve puts it back into heating mode. That's to drop that head pressure that rises during a defrost. And if you were to cut this jumper that says soft SW, now that switchover delay would go to 0 seconds, where the fan and the switchover would happen at the same time. There's also a low ambient heat pump lockout at -12 Fahrenheit. So what that means is at -12 Fahrenheit, if it receives a Y signal, it will not run the outdoor unit, but it will put a signal back out the X2 terminal. And the X2 is going to be hooked up to your W on your indoor unit, and it's going to turn indoor heat on. It's not going to resume heat pump operation until it rises to -3 Fahrenheit. So if you have a heat pump that you give it a Y signal and it doesn't turn on, you may see a soft lockout error code on your fault light. You might want to look at the calibration of your outdoor ambient. And if you give it a Y signal and your furnace turns on, same thing. And then the other thing is the low pressure cutout bypass in defrost. What that means is that the low pressure cutout is not going to do anything. It's going to completely ignore the low pressure switch for 3 minutes during a defrost. So the sequence of operation, we've got our defrost board here, wiring in the outdoor unit here, air handler terminal strip here, and thermostat terminal strip here. So first we're going to give it 24 volts on R and common on B, and we're going to see a green LED flash. That's that status light that I pointed out earlier. Once it's powered up, the board is going to create 3.3 volts DC, and it's going to put that through the LPCO, and it's going to verify that's closed. It's also going to put 3.3 volts DC into the two thermistors, the coil base sensor and the outdoor sensor. And then depending on what voltage it sees come back is what temperatures it's reading. So now we're going to give it a Y signal. So Y is going to come through here. It's going to go through the K3 relay, which is normally closed. That has the ability to intercept the Y signal before the contactor. It does have a 1 minute compressor on delay if the compressor has been running for the last if the compressor just shut off, it won't turn back on for another minute. So you can't do short cycles. So now that Y signal went through the K3 relay on the defrost board, came out here, goes through your high pressure cutout, and if you have a snap disc on your discharge line, through there as well. And now it's hitting the coil for your contactor that turns on your fan and your compressor. Now we're in the normal heating mode of operation, so we're potentially developing frost, and when it's time to enter a defrost, now you're going to see the K1 relay on the board close, which will energize the reversing valve, putting the refrigerant in the opposite flow of direction. So now the outdoor coil is warm and the indoor coil is cold, absorbing heat in that indoor coil and putting it into the outdoor unit. It's also the same K1 relay puts 24 volts out X2, which is going to go to your W's on your indoor unit. This is going to run your electric heat or your gas heat, which just tempers the air so that cold air isn't coming out of your ducting during a defrost. Your outdoor fan is also going to turn off because you're warming up that outdoor coil and you don't want to be fighting cold air going across the coil. So it's going to continue to defrost for a minimum of 1 minute, and then once that coil sensor reaches 47 Fahrenheit, it's going to terminate the defrost. And the first thing that's going to happen is it's going to turn the outdoor fan back on, because without the outdoor fan running and it essentially being in cooling mode, our head pressure is going to shoot up fairly high. So it turns that outdoor fan on to reduce head pressure. 12 seconds later, it's going to remove the switchover valve call. So now it's going to go back into the flow of refrigerant is going to go back into heating mode. Now it's back into the normal heating mode of operation. So a couple of tidbits here. The green light flashes when you have R. So say you don't have enough wires and you decide, okay, I'm not going to use R, I'm just going to twist Y and R together. That would mean that the board is only powered up during a call for heating or call for cooling. So it's not going to be able to develop that adaptive intelligence, because the board is going to completely erase with every single cycle. Another thing is maybe you don't have R on there at all. It's still going to work without R hooked up. The outdoor unit is still going to run, but it's never going to go into a defrost, because R is what's powering all the logic in here. So the green light, if you don't have a green light, you don't have R hooked up, or there's an issue with the R wire. Some of you may remember these larger defrost boards. This is what the newer defrost board looks like, which we went over.
Kristian, Wayne had one question about the W wire going to X2 goes to W1 on gas.
Yes. So X2 is going to go to W1 on gas. And what that does is two things. When you have a low ambient lockout, it's going to lock out the compressor so the heat pump can't run below -12 Fahrenheit. And it's going to send X2 back to W1 so that Y signal goes to the outdoor unit, doesn't turn the outdoor unit on, comes back and turns the furnace on during that lockout. The other thing it's going to do is during a defrost, it energizes X2. So that heat developed from the gas furnace is going to go into that indoor coil and really help with a defrost by adding so much heat to the refrigerant. The other thing it's going to do is during a defrost, that indoor coil is really cold, absorbing that heat. And without indoor heat running, you're gonna have cold air coming out of the ducts. So it tempers the air coming out of the system. See, Wayne's still typing. So we have our old board and we have our new board. So this is what the old board looked like. Oh, W2 on electric. That's just to temper the air, because that electric heat is downstream of the indoor coil. So the electric heat is just to temper the air so that cold air doesn't come out of the vents. It doesn't help with the defrost. If it's not a concern of the homeowner or yourself, you know, electric heat does cost a bit to run. That would be your choice if you wanted to remove that. I would put it on W1 and W2. Put it on that higher stage. So we've got the old board. It's a large board here. New board. It's a small board. A few changes. That low ambient lockout on the old board was -7. It's now -12 on the new board. Low ambient resume was +3. It's now -3. So they're running the heat pumps a little colder. The other thing is we saw some nuisance low pressure cutout trips with the older board. So it used to ignore the LPCO for 1 minute, and now it's ignoring it for 3 minutes. So if you do have a system where you have random LPCO lockouts on a heat pump, and you've checked that your charge is correct and everything else is running properly, you may want to just put a new board on it. don't go to the new board right away. Verify everything else is working properly first. So verifying those sensors, in Service Facts, you're going to see a chart. It's going to have temperature in Fahrenheit and Celsius that goes along with a resistance, because these are thermistors. And if it's connected to the board, you would use volts DC, and I'll show you guys that here in a second. So what I recommend is put your sensors in ice water, fill the cup with ice or vessel with ice, and backfill with water. Then you know that it's 32 Fahrenheit in that cup, right? So you're doing two things. You have a calibrated testing media that you've put them in that you know is 32 Fahrenheit. The other thing you're doing is you're submerging those sensors, which verifies the integrity of the epoxy in that sensor. Because sometimes we see sensors where they test out just fine, and then when the coil starts condensing and has some liquid on it, that liquid gets into the sensor and the sensor fails. And when you're there, the sensor is dried out again and it looks like it's just fine. So just submerge it in water, make it ice water so that you know it's 32 Fahrenheit. And as long as it's between the numbers for 30 and 35 Fahrenheit, you're good. With the exception that if one is at 35 and the other is at 30, then you may want to change one or both of them, because you want those sensors close to each other as well. Because it is a delta that triggers the defrost, and if you already have a delta or have a delta the opposite direction, then it may have to get colder in order to initiate a defrost. So each sensor needs to be between here, and I would say within a couple degrees of each other as well. And the test points for testing voltage. Here you have a test pad for 3.3 volts DC, which is the source voltage for those sensors. You would test that against ground, because this board takes the 24 volt AC and turns it into 3.3 volts DC for your sensors. And then you also have test pads for your coil temp sensor and your ambient temp sensor, and you would check those with DC volts to ground and look at that versus this chart on the DC volts. So DC volts is connected to the board, and ohms is when it's removed from the board. If we want to check our voltages, the first thing we're going to want to do is set our meter to volts DC. Put one side on ground, and you can check your source voltage at the 3.3 volt test pad. We verified we have 3.3 volts DC, which is our source voltage going to the sensors. Then we can move to the coil temp test pad. We're seeing 1.4 volts DC, which is roughly 32 Fahrenheit. Because in your case, you're going to have these sensors submerged in ice water. In my case, I just have it set to 32 because it's a rheostat. And then you've got the outdoor ambient temperature. It's also at 1.4 volts DC. So in this case, we verified that the source voltage is good from the board, and we also verified that if the correct voltage is coming back, then the resistance is also correct. We could do that same check by putting our leads at the back of the, in this case, the outdoor temperature sensor being black wires, 1.4 volts. Yellow wires being the coil bottom sensor, we have that same 1.422 volts. If the voltages were incorrect, we would switch to resistance, pull it off, and check the kiloohms through the sensor. In this case, we have 32.23 kiloohms. We would reference that chart to see if that's the right kiloohms for the temperature that it is. And that's how you verify the calibration of the sensors and check the voltages through the board. My preference is to check the voltages through the board because you're seeing what the board actually sees, and you're testing the board and the entire system as plugged in. So that's how you test your sensors. One really cool thing that Link is bringing is if you're on Trane Diagnostics, you'll be able to see the outdoor temperature here. You'll also be able to see the outdoor coil temperature here. This will be on all of our Link variable speed equipment right now, so it does have to be communicating. So for troubleshooting, you might be able to tell which of these sensors, if any, have failed before you even get to site. So what you could do is look at the weather app on your phone or online and go, okay, I know that it's this temperature outside. The outdoor temperature sensor is relatively similar to that, and the outdoor coil temperature sensor is the same as well. Now you're going to have to pick a time where the system hasn't run for a while. So if you were to pick somewhere around here, you would verify that these are the same temperature. So just another way that Link is going to help us with some troubleshooting down the road. So here's a reversing valve, the inner workings of the reversing valve. You can see that this solenoid where your O is hooked up to, all it does is change refrigerant flow in this valve right here. And then it takes and it'll route your discharge pressure to one side of this and your suction pressure to the other side. So it moves this shuttle back and forth. So you do need to have a delta from your discharge to your suction in order to move this shuttle over to change your flow of refrigerant. So if you do have, we talked about the outdoor fan turns on for 12 seconds to reduce head pressure before the switchover valve is disengaged. So if you do have switchover valves sticking in cold temperatures, getting stuck part way after a defrost, that's where you would cut that soft switchover so that it disengages the heat pump, or sorry, the reversing valve when there's that high delta T. So as shown earlier, this is the jumper you would cut for that, and it would remove that 12-second delay from the fan coming on to the switchover valve. Your termination temperature, we talked about how factory is 47. When you cut it, it's 70. That's the temperature that the defrost terminates at. So if you cut this, it's going to go from 47 to 70. To force a defrost, you would jump these two wires, jumpers. We're going to go through the sequence of operation. First, we're going to give it a Y signal, which immediately turns on the compressor and the outdoor fan. So now we're in the heating mode of operation. The outdoor coil is getting cooler so that it can absorb heat energy from the outside air. At the same time, it might be building frost. So we're going to put it into a defrost mode by jumping these two forced defrost pins. You're going to immediately see that the reversing valve is now energized, changing the flow of refrigerant. So the indoor coil is now the cold coil, absorbing heat energy from inside, putting it into the refrigerant, and making the outdoor coil the warm coil to help melt that frost. You'll also see that the fan was shut off on the outdoor unit. This is so that the cold air going past the coil isn't fighting your defrost. And you'll also see that the X2 was illuminated because X2 is going to go to your W on your indoor unit, so that during a defrost, either your furnace heat is going to come on or your electric heat in your air handler is going to come on so that cold air doesn't come out of your vents. So this defrost cycle is going to last until the coil sensor reads that it's gone above the termination temperature, factory being 47 Fahrenheit. So we're going to adjust that above 47 Fahrenheit, where we see the outdoor fan came on. That's going to lower the head pressure that's been building up during the defrost. So it's not such an aggressive switchover. That's going to be for 12 seconds before the reversing valve is de-energized, as well as the X2, putting it back into the normal heating mode of operation. If you don't want it to turn the fan on 12 seconds prior to your reversing valve being de-energized, you can cut this soft switch jumper. And if you want it to terminate the defrost at a warmer temperature of 70 Fahrenheit versus 47, you would cut this jumper. So when you have a heat pump outdoor coil, you do have essentially more than one coil to make up the coil. So in this case, you can see 4 coil circuits. It's like 4 separate coils to make one coil. So coming out of the TX valve, we've got our distributor, comes out to 4 different coils. And then we have a header at the end of them to tie them all together. Now, most outdoor coils you're going to see have about 6 circuits, and not all circuits will be the same. So in this case here, the top is frosted, but the bottom is not frosted. So we know, here's our coil base sensor right here, and you can see that that's only on the bottom coil circuit. So it's not measuring anything on this coil from here up. So with this being frosted up, but this not being frosted up, the defrost board thinks that the coil is frost free because the bottom is. So in this case, you would probably want to be checking the temperature of each of these separately, and each of the distributor pipes separately. And if you have a big delta between any of your coil circuits, say more than 10 degrees Fahrenheit, then you have unequal coil circuits. And you could move this sensor to the coldest circuit, and that may fix it. If that doesn't fix it, you may have to look at changing the outdoor coil to fix the defrost issue. Usually moving the sensor to the coldest circuit is going to do the trick. But when you see banding like this, often that's going to be charge related, where low charge can cause banding in a lot of cases. So look for how even it is. If you see it building up from the bottom up, that's probably a drainage issue. This one's up on, it's raised up, so the water that comes off of it has somewhere to go, and the snow isn't building up on the side. But if it's building from the bottom up, that's often a drainage issue. So we talked about low charge. How do you verify charge? Well, the only way that we recommend to verify and adjust charge is by subcool if you have a TX valve in your indoor unit, or by superheat if you have a piston in your indoor unit. It has to be above 55 Fahrenheit outside, and your indoor temperature has to be between 70 and 80 Fahrenheit. But if you're seeing frost issues, it's probably not above 55 Fahrenheit. So what you can do is in the second to last page in service facts, you would see this chart, and this would be your heating pressures. So we have 3 lines here. This is your high side pressure, and this line would be if it was 60 Fahrenheit in the house. This is 70 Fahrenheit in the house, 80 Fahrenheit in the house. So if it was, say, 35 Fahrenheit outside, 70 Fahrenheit in the house, you would be looking at about 345 PSI head pressure. Your suction side, you still have those same 3 lines, but they're so close together it looks like one thick one. On your low side, which you would be measuring just below the reversing valve inside the indoor unit, there's a port there that you would be checking from, and you should see about 85 PSI. So if you have the correct PSIs per this chart, you probably have the right amount of refrigerant in there, and I'd probably start looking at other things. Usually the first thing I do during a defrost troubleshoot is put it into a forced defrost and see what happens. First, I'm going to see, okay, when I force a defrost, does it go into a defrost? If it does go into a defrost, does it melt that ice? If it melts all the ice, you probably have something going on with your sensors or defrost board because it's not initiating a defrost. If it goes into a defrost and doesn't melt the ice, you know, maybe it's a charge related issue or metering device or something else going on. But if these pressures match what you have in the charts, I would probably move on. But if they don't, you can't adjust charge based on these pressures. These are just for reference only. The only way that you can charge in heating mode when it's below 55 outside is way in and way out and come back in the spring and adjust via subcool. If you're off, I wouldn't immediately jump to adding or removing refrigerant or doing a reweigh. I would take a look and go, okay, I'm high on my pressures, so maybe take a look at the indoor side, because if your pressures are high in heating mode, that's going to be an indoor issue probably. So I'd be looking at the indoor filter, dirty indoor coil, indoor airflow, things like that. If you're troubleshooting a defrost, chances are you're seeing low pressures as compared to this chart. Again, I wouldn't immediately just add some charge. You know, is the outdoor fan running? That's going to make your pressures really low. Is the outdoor coil really dirty? That's going to make your pressures low. Or is it frosted up? Is there ice all over the outdoor unit? And maybe you don't see it because the louvers are covering the coil. I've seen it many times where we have really low refrigerant pressures, but then we do a few forced defrosts and now the pressures look good. So then we got to look at something else. So don't adjust based on these. They're for reference only. We have a nice data sheet. If you reach out to anyone on the FSR team, we're more than happy to provide you with this. Because if you go to site and you leave before you've positively identified the issue, it's hard to troubleshoot later. So we do have this where it's got the model, serial number, return air temp, discharge temp, heating CFM, total external static pressure, some line set information, outdoor unit information, different line temperatures, subcool, superheat, outdoor temp, also individual temperatures of all of these tubes that we talked about on the coil, also your sensors, your ohms, your DC volts, and the temperature, and we even provide the chart. So we have this in Excel, and it'll really help you with the troubleshooting process if you're troubleshooting a defrost problem. But also if you are troubleshooting one and you don't positively identify the issue, filling one of these out and taking some pictures of the general install and sending that to the FSR team is really going to help us, because these are the questions we're going to be asking first. And without these, we're likely going to be asking you to go back and take a look. So here's where we want those pictures of the outside. You know, here's a good example. We've got water coming off the roof right onto the outdoor unit. That makes it look like this, right? And that's why we want to see some really zoomed out pictures so we can see what's above it, what's around it. Here's one that I like. Here's a road sign, and I've seen this driving through Chilliwack before, where you've got rain that freezes immediately. Now, this sign isn't a heat pump. This sign isn't getting colder than outside temperatures, yet ice is building up on it like crazy. If you have a weather event like that, it doesn't mean that the heat pump is broken. It just means you had a strange weather event, thaw it out, and keep an eye on it. It doesn't mean that anything is broken. Here's one where snow has blown onto it. Here's one where water was dripping onto the top of this unit, blocking all this. So this is where application and environment can play a big part, and why we would want to see that data sheet as well as some pictures. We're also going to be looking for, is the unit raised up off the ground? Can it drain properly? Another thing that we'd be looking at is, say it's a side discharge unit and it's up on top of a commercial building's roof. Remember we said that the outdoor fan has to stop so that it gives the coil a chance to warm up and it's not fighting the cold air rushing through the coil. Well, if it's on a roof, you might need a wind baffle or something like that, because if you've got it on a roof and you've got prevailing winds blowing through it, it doesn't matter that outdoor fan shut off. With those prevailing winds going through it, it's still never going to be able to defrost. So you may need a wind baffle in that case. Going through the error codes on the defrost board, a 1 flash means that you have, and these are the red LED next to the green one. 1 flash means ambient temp sensor is out of range. So it doesn't mean that it's out of calibration. It means that it's a direct short or completely open. In that case, it's going to initiate a defrost every 60 minutes of runtime. And defrost will terminate on coil temp, because we still have the coil temp sensor, we just don't have the ambient to reference it against. So a 2 flash means the coil temp sensor is opened or shorted. Again, it doesn't mean that it's out of calibration, it's a direct open or short. And it's going to initiate a forced defrost for 15 minutes every 60 minutes. A 3 flash means the low pressure switch is open. The LPCO is the only thing that can initiate a hard lockout, which requires a power reset of the indoor unit, because the defrost board gets all of its power from the 24 volts from the indoor unit. So a first trip is going to be a 15-minute soft lockout, where you're going to see a 5 flash. Second trip, 30 minutes. Third trip, 45 minutes. Fourth to eighth is going to be 18 hours each. And once you hit 9 trips, you're going to have a hard lockout, which will give you 4 flashes. And LPCO is the only thing that can cause a hard lockout on our heat pumps. 6 flash, this means your defrost cycles are too close together. If they're within 15 minutes of each other, often you're going to see a 6 flash associated with low charge. That's usually the biggest reason, because it's not low enough that you're going off on low pressure cutout, but it's low enough that outdoor coil frosts up very quickly. 7 and 8, this just means that after a defrost, we're not seeing this delta happen. So this, if you see a 7 or 8, it's not going to affect the operation, but it's going to trigger you to check calibration of both those sensors, the coil and the ambient. Nine flash, this is a low ambient soft lockout. So at that minus 12 Fahrenheit, it's going to lock out the outdoor unit and send a signal back to the indoor through X2. And in that situation, you're going to see a 9 flash. So if it's, plus 5 Celsius outside, and you see a 9 flash and your heat pump won't work, I would say that you're going to want to be looking at your outdoor temperature sensor. Its calibration would be the first thing I'd want to look at, because the outdoor unit certainly thinks it's minus 12 Fahrenheit, and if it's raining outside, then it's probably not minus 12 Fahrenheit. So a 9 flash, if it is below 12 Fahrenheit, it's just doing its job. If it's not below minus 3 Fahrenheit, then you're going to want to check the calibration of that sensor. So, any questions?